Hello friends, Savitribai Phule, Pune University, TYBSc Physics Special, Paper 2. In the series of this video lectures on multiple choice question, this is my second lecture, video lecture on multiple choice questions of special theory of relativity. In short, we call it to be STR. Please note, this is one of the very interesting conceptual chapter wherein several different types of multiple choice questions can be asked. Most of the questions will be based upon concept. Some of the questions will be based upon very simple calculations. So let's carry out such 40 questions, simple questions, multiple choice questions, which may be asked in the forthcoming SPPU semester 1 examination. So let's go for these questions one by one. In the series earlier lecture we have seen this curvilinear coordinate system questions over that. I hope you would have enjoyed these questions, you would have liked this particular video, and now this is my second video wherein I am putting some questions on this particular chapter, that is special theory of relativity. Now in this particular case of special theory of relativity, first we have to understand what are the postulates. Based upon these postulates, we have to go for understanding this Michelson-Morley experiment. Actually, this postulates comes after this existence or the proof of this Michelson-Morley experiment. Apart from that, we need this Lorentz transformations. From that, we need law of addition of velocities. Also, we need to understand the expression that is called as relativistic mass relation. That is m is equal to m0 upon square root of 1 minus v square upon c square, or mass energy equivalence relation, that is E is equal to mc square. Then a relativistic energy, classical kinetic energy, interrelationship between them. How to write momentum in case of this relativistic mechanics, that is also important thing here. At the same time, we are needed to go into details of this four-dimensional space, that is called as Minkowski's force space, or that is called as space-time continuum. So these are the few important points wherein we can concentrate on this particular chapter to solve some of the important MCQs which have been asked for as follows. Now let's go for the first one. Number 1, according to the special theory of relativity, physical laws are the same in frames of references which, there are four options given. Option A is move at uniform velocity. Option B is accelerate, that means they do not move with the uniform velocity. C is move in circles, and D is move in ellipses. So out of that, we have to just concentrate. Correct answer is A. But from where this comes, that is what we have two different postulates. So we have postulates of this STR. I'll just go for in brief what these postulates are. The postulates are as follows. First postulate tells you the laws of physics must be identical in all inertial frames. All inertial frames of references. This is our first postulate. Laws of physics must be identical in all inertial frames of references. And second, velocity of light, that is C, is constant for all observers, irrespective of their motion. So whatever may be the motion of the observer, velocity of light measured by any observer is always found to be constant. So that is the second postulate. And first postulate is this inertial frames of references, and we know that from our definition, the frames of references which are moving away from each other with certain, this is what we draw several times, this diagram. This is my x, y and z, and this is another frame, x prime, y prime, z prime. This is the frame which is moving away from the first frame with certain uniform velocity. So all such frames of references which are moving with uniform velocity from each other are called as inertial frames of references, and laws of physics defined in all such inertial frames of references must be identical. This is what our first postulate, and therefore question number 1 correct answer is this E. This is what reasoning we can provide. This is according to this first postulate of the special theory of relativity that tells you the laws of physics must be identical in all inertial frames of references. That's what this is the definition of inertial frames of references. These are the postulates and we have to correlate them as to our options given here. Now question 2. Clocks in motion moving reference frame compared to identical clock in stationary reference frame appear to be slow, okay, appear to run. Okay, so now there are 4 options: slower, at the same rate, faster, and backward in time. So don't use your common sense there. Now this is what I am having, again a frame of reference, inertial frame of references. This is my frame S, and another frame which is moving away from the first frame with the, this is what S prime frame, and this frame is moving away from the first frame with velocity v, uniform velocity v. There are 2 clocks. One clock is kept here and there is another clock which is kept in the second frame of references, and as per this concept of time dilation we know that the time measured by observer in frame S prime, this T prime, will be given by time measured by observer in frame S divided by square root of this factor 1 minus v square upon c square, where v is the relative velocity. Now this T prime will be bigger because this root of 1 minus v square upon c square is going to be fraction all the time. That's how the second or the duration of the time measured by observer or clock in moving frame of reference will be bigger, or time duration will be bigger. That means it will measure its time at slow rate, and therefore correct option of this question number 2 is slower. The clock in motion is always runs slow. It measures time at slow rate. That is to be understood, and that principle is called as time dilation. So clock in motion runs slow. Okay, so clock in motion runs slow. Okay, so this is to be understood and know, and based upon this there can be several different types of questions can be framed or designed, and that this important fact we should understand, we should mention all the time, we should know all the time. Whenever there is a clock in motion, that clock runs slow, it measures time slowly, and this particular effect is called as time dilation. Now number 3, question 3, a spaceship moving away from the earth at the speed of 0.9 c. If I go draw for this diagram, this is the earth and the spaceship is moving away from this earth with a speed of 0.9 c. It fires a light beam backward. So it fires a light beam backward which is having velocity equal to c. An observer on earth would see the light arriving at a speed of, so this is the observer on the surface of earth, he will measure the speed of light which is arriving at his end towards him from that particular satellite or that particular spaceship. And here we are not needed to calculate by using our algebraic method. This is what the principle that is called as the again the second postulate of STR comes here in place. So whatever may be the direction of that particular spaceship, whatever may be the direction of that particular observer or his speed, it doesn't matter. Velocity of light measured by anyone will be always same, and hence the options given, there are 4 different options given. This option is not correct, even this option is not correct, this option is also not correct. So velocity of light is always remain constant or found to be constant for all observers. So in this case we are not needed to do any algebraic calculations. We have to always remember that velocity of light is maximum for all observer and it is always constant whenever whatever may be his motion, direction of the motion, nothing counts. So velocity of that particular light always remains constant. This is what the second postulate of STR. Based upon that, this question number 3, correct answer is always C. Whether this spaceship is moving towards Earth, whether it is moving away from the Earth, or it is moving in the perpendicular direction to this particular direction, doesn't matter, as long as this light is emitted by this particular source, and wherever it is going,
it doesn't matter. The velocity of light measured by an observer on the surface of Earth would be always constant, and that is C. Therefore, the C is the logical and correct answer of this question number 3. Okay. Now question 4. The term relativistic refers to the effect that are, okay. So that is what we divide physics into different branches. That is, one is called as non-relativistic physics and second is called as relativistic physics. So this is again a logical definition. There are 4 options. The term relativistic refers to the effect that are: option A, observed when speeds are near the speeds of light; B, noticed a moving object; C, observed when objects move backward in time; and D, measured by stationary observers only. So out of that, all these 3 remaining options, B, C and D, are incorrect. They are not describing exact term. What do you mean by relativistic effect? So the term relativistic effect refers to the effects that are observed when the speeds of an object approaching to the speed of light. So whatever physical phenomena that are happening at the speed of light, all these phenomena are called as relativistic phenomena. So the physics of the objects at very low speed, that means Earth, the speed of Earth around Sun, or if a car is moving on the surface of Earth, that is called as non-relativistic effect. So when in this case the speed involved is much less than this velocity of light, so this is the case that is called as non-relativistic physics. So all the phenomena that are taking place with very ordinary velocities much less than as compared to velocity of light, all these called as non-relativistic. And then this velocity of the object, whatever may be object, microparticle, macroparticle, whatever, when this velocity of light is not reaching C but approaching towards C, the effect or phenomenon observed at that time is called as relativistic. So anything or any phenomenon that is happening because of this reason or at this particular stage, where this velocity involved in the phenomenon are approaching the velocity of light, then such phenomena are called as relativistic phenomena. And therefore, theory of relativity is also a physical phenomenon that is observed at the in the range of whenever we are reaching to the velocity of light, and that's what in ordinary physics or in an ordinary velocities this relativistic effect are usually are not observed. So such type of effects are observed whenever we are approaching to the velocity of light. So this is again a conceptual question which is having a very simple answer. Now question number 5. The purpose of Michelson-Morley experiment, or that is called as MM experiment. This experiment was basically done. There are 4 options given. Option A, to determine the velocity of light. Option B, to detect possible motion of Earth relative to the Sun. Option C, to detect possible motion of Sun relative to the ether. And option D is to detect possible motion of Earth relative to the ether. Now this is what the correct option in this case is D, because we know according to this electromagnetic theory or Maxwell's electromagnetic theory, we know that light is required to have a medium for its transfer of energy in the form of electromagnetic waves. We require this type of medium that is called as hypothetical medium, which is called as ether. So it was thought in this particular electromagnetic theory, ether is present everywhere in this universe at all locations, and light radiations require this type of hypothetical medium to travel from one location to another location. And this ether medium, that is what the concept that was from the classical physics. And relativity theory directly questions this particular concept of this existence of ether to such test the existence of ether to calculate the velocity of Earth with respect to ether. Such experiment was done, and that's what the correct answer of this experiment is this, to detect the possible motion of Earth related to Earth. And fortunately or unfortunately, let's say that this experiment has found a negative result. It has discarded the concept of ether. So such ether is hypothetical, ether is not required or is not present anywhere, is not observed at all, which is not having any of the physical properties as what we have seen. So the existence of ether was discarded by the negative result of this particular experiment. and that led Einstein to put his postulate, the second postulate of relativity, that the velocity of light is constant for all types of observers or all observers. So this Michelson-Morley experiment, its outcome or the actual experiment, this experiment, the construction, its design, its working, its outcome, its result, etc., etc., everything is important. And what is more important is that this has discarded this existence of ether. In other terms, we can say that it has discarded the existence of the universal frame of reference. If such type of frame of reference is not existing, then this is another implication of that, is that velocity of light must be constant for all observers irrespective of their motion. And that's how this second postulate of relativity is the direct consequence of this Michelson-Morley experiment or negative result of the Michelson-Morley experiment. So that has to be remembered, and then we can go for understanding of this importance of this experiment and all these things. So that is all question number 5, which is related to Michelson-Morley experiment. Now, next onwards, question number 6, we have to calculate something, that is, we have to go for some calculations. Question number 6. A spaceship approaches the moon traveling at a speed of 0.5 c with respect to the moon. Its crew shines a laser at the moon. The beam strikes a lunar mirror and is reflected back to the ship. The crew on the ship will measure the speed of the reflected beam to be as long as. So remember, again, there is no need to do any calculation. You can assume that this is the situation. This is the moon here. There is a this is the one spaceship that is traveling towards moon with this speed of 0.5 c. It flares a laser light with a speed of 1 c. That is, a mirror is kept here, and again this beam falls here and gets reflected back. And now what will be the velocity of this radiation or this laser beam according to an observer on this particular spaceship? So again, this is not no need to do any calculation here. Once we understood that this is again a direct consequence of the second postulate of STR, special relativity, that velocity of light, laser is also a one of the form of light. So velocity of light is constant for all observers independent of their motion. So whatever may be the situation given, whatever may be the motion of that particular spaceship, whatever may be the mirror kept on the surface of the moon, doesn't matter. Every time the velocity of the light radiation approaching toward the spaceship, which is reflected from the moon surface, that must be again equal to the velocity of light, that is equal to c. And that's what the correct option of this question number 6 is, C. So whatever numbers you have been given here, whatever situation you have been given here, doesn't matter, as long as we are measuring, anyone else is measuring velocity of light in any direction, whatever may be the source, whatever may be the measurement instrument required for used for measurement, doesn't matter. Velocity of light c is always found to be constant for all observers, and this is what our second postulate of relativity. So this question number 6 is directly associated with this particular second postulate of STR, that velocity of light is always found to be constant for all observers. So you have to just use this trick and get the answer of this question number 6, that is C. No need to do any calculations as here. Now question 7. A train has rest length 100 meters. So this is the train which is having its length to be 100 meter and traveling a very high velocity. If it goes through a tunnel of length 80 meter. Now this is the tunnel having its length to be 80 meter. This is tunnel and this is your train. This train is traveling with a very high velocity and this is passing through this tunnel. So tunnel, observers located at both ends of the tunnel note that at one instant the train appears to be exactly fit within the tunnel. So as this train is traveling through this tunnel, at one instant this observer finds this train length is of 80 meters, that is, it is completely engulfed by this particular tunnel. And at what speed? So what is the speed required for this train to appear to be its length to be 80 meter rather than 100 meter for this observer? So observer is here who is observing motion of this train. at one instant it observes that even though the train's length is 100 meters, it is passing with such a speed that when it is passing through this tunnel, its length is found to be only 80 meters. Then what is this value of V? This is to be calculated. So here we have used very simple formula, that is called as length contraction, which is given by L is equal to L0 into root of 1 minus V square upon C square. Remember, this L0 is called as length at rest and this is length in motion. So we have to calculate this. L is equal to L0 initial given is 100, root of 1 minus V is to be calculated, that is what we have to calculate, V square upon C square. So max square of this, I'll get 100 upon L is equal to root of 1 minus V square upon C square. This is not, I don't should write this. So this is L, okay, and we have been given this L. L is given to be 80 meters. L0 is going to be 100 meters. So replace this values. Therefore, it is 80 upon this is 100 is equal to root of 1 minus V square upon C square. So I can cancel of this. So it is 8 upon 10 or root of 1 minus V square upon C square. That can be written as 4 upon 5, or I can write this as 1 minus V square upon C square, max square of this. So it will become 16 upon this is going to be 25. Therefore, V square upon C square, if it is taken here, it will be 1 minus 16 upon 25. So this is 25 minus 16 upon 25. So that is simply 16 and 25, difference is 9. 9 divided by 5, and therefore V square is equal to 9 upon 5 times C square. Taking its square root, I'll get V is equal to square root of 9 is 3, square root of 5 is root 5, and this is now going to be square root of C square is C. If I go for this calculation, 3 upon root 5, so use this calculator and go for this calculation, this will come to be 0.60 C. So the correct option of this answer is going to be 0.60 C. So this much should be the velocity of the train that is passing through this tunnel to appear its length to be shortened up to 80 meters by as observed by this observer, and therefore this entire calculation, if it is calculated, you will find this to be 0.60 C. So go for actual calculations. 3 upon root 5, you will get 0.60. So the correct answer of this question number 7 or 8, I think, 7 is D. It is 0.60 C. So there can be you can use other methods. Instead of making this to be 4 upon 5, let it be 8 upon 10. If it is done this way, we are not needed to go for this calculation. So it will be now, then 1 minus V square upon C square will be 64 upon 100. Then if I go for this V square upon C square, this is 1 minus 64 upon 100. So it is 100 minus 64 upon 100. So it is 36 upon 100. And therefore V square is equal to 36 upon 100 into C square. Getting its square root, as we know, its square is 36. So this is going to be 6 divided by this is 10 multiplied by this is C. So getting its square root, I will get this, and 6 upon 10 is again 0.6 times C. So either you go by this way or you go by this way, what we have shown here. Doesn't matter, I will get same answer, that is to be 0.60 C. So this is again one conceptual problem. Once we understand this concept of length contraction, that this train in motion appears to be shorter than its length, original length is going to be 100 meters. When it is passing through this tunnel, it appears to be of the length of 80 meters. Then what would be the speed of that train? It has been calculated. So use this formula and get the correct answer of this question number 7, that is D, 0.60 C. Now, this is one more. A starship alpha is traveling at 0.8 C. Gamma this time is given, is 1.1, this is not Y, this is gamma, 5/3. With respect to the identical starship beta, each starship has its rest length of 10,000 meters. The ship's engineer aboard the beta measures the length of the alpha as it passes by his window. what result should he get. Okay, so here also we have to use the same concept. What, see here, in this problem we have been given this gamma, and gamma is defined by 1 upon square root of this 1 minus root of v square upon c square. So 1 upon root of 1 minus v square upon c square, this is defined to be gamma, and this is given to be simply pi u upon 3. Now in our problem, again we have to use this factor, this formula. L is equal to L0. Now this is the length of the spaceship alpha measured by an observer in the spaceship beta, and this is going to be L0 times, this is root of 1 minus v square upon c square. So if I go for this calculation, so from this I will get root of 1 minus v square upon c square is equal to 1 upon gamma, and therefore it is root of 1 minus v square upon c square is nothing but 3 upon 5. So I can use this simple calculation here. There is no need to calculate the root and everything there. So L is equal to L0 is given to be 10,000 meters. So this is 10,000 meters into 1 upon gamma. So if it is given root of 1 minus v square upon c square, it is 1 upon gamma. If it is given 1 upon root of 1 minus v square upon c square, this is simply gamma. But I need this quantity to be root of 1 minus v square into c upon c square in the numerator. Therefore, this is 1 upon gamma, and 1 upon gamma is nothing but 3 upon 5. If I do this calculation, this comes to be 2000 and multiplied by this is 3. So exact answer, this is going to be 6000 meters. So that will be the length of spaceship alpha measured by an observer in spaceship beta, and this length will be appear to be shortened, and therefore from 10,000 it appears to be 6000 meters, and therefore correct option or answer of this question number 8 is A, that is 6000 meters. So instead of using this numbers 0.8c or whatever, we are not needed to go for this calculation. In some of the problems you will be directly given gamma. So this gamma is nothing but, gamma factor is nothing but 1 upon root of 1 minus v square upon c square. So use this factor very nicely to reduce your calculation as much as possible. And as in this example, it shows that this L appears to be simply 6000 meters and not 10,000 meters. This is what is a length contraction for an observer in the spaceship beta. Now this is again a tricky question related to the postulate of this STR. So question number 9, a spaceship moving towards the Earth at a speed of 0.9 c shines a green laser. It was again related, same problem what we have seen earlier. Green laser at an Earth. An observer on the Earth would see the light arriving at a speed of. So naturally, again, this is going to be exactly similar problem what we have seen earlier. This is also related to the second postulate of relativity. So velocity of light is found to be the same, that is c, and at this time, as this is what a Earth here, and this particular shape is moving towards Earth. So whenever it is approaching, in this case, there is a just like when this object is moving away, we call it to be red shift, and when this particular observer is approaching, object is approaching toward this Earth, we are calling it to be violet shift. So this laser which is green here, laser which is green in color here, this particular radiation approaching towards Earth, its velocity must be constant to the velocity of light, will be same to the velocity of light according to the second postulate of STR, but its wavelength must go on decreasing because it is going towards violet shift. So there will be some shorter wavelength, and hence correct option of this question number 9 is B. It will be of shorter wavelength, but the velocity of that must be same, that is equal to c. So there should not be any change in velocity, but there should be change in the wavelength, because this is the case of violet shift. In Doppler effect also we have seen that this particular fact, the star which is moving away from the Earth, the radiation observed from that particular star is found to be redshifted, that is called as redshift. Or when this star is approaching towards Earth, and whatever light emitted from that star appears to be shifted toward this violet end, that is called as violet shift. So same concept is applied here. Doesn't matter, velocity of the star, light approaching or receding star is always found to be equal to velocity of light, and it is going to be red shifted or blue shifted or violet shifted. But this is again a conceptual problem, example number 9. Now this is question number 10. Again, this is related to something very interesting concept. The decay of sample of radioactive atom is studied by observers moving in different ways. So there are several observers in 3 different types of motion. One moves at 0.8 c, another at 0.5 c, another at 0.25 c, and one at a speed 0. That means this particular phenomenon is observed here. There is observer 1 who is not moving, so its velocity is 0. Then this is second observer who is moving with velocity 0.25 times c. There is another observer who is moving with velocity that is going to be 0.5 c, and last one is who is moving away from this. It is 0.8 times c. Now you will find what we have to do. These are different. The one with the speed of dash dash will measure shorter half-life. So this is again, if we are going to measure the time dilation, we are going to measure the duration of the second. You will find for him this second will be exactly equal to 1 second. So second of this is 1 second. Now second of this will be longer than this. So this is longer here. Then second measured by this observer, which is in the motion of 0.5 c with respect to that particular object, radioactive substance kept on the surface of Earth. His velocity or his second will be still more or longer than the second of this as well as this, and his second, the last observer which is moving away with 0.8 c, his second will be larger. So this is second 1, second 2, the second observer, third observer, and fourth observer. So his second will be larger, duration will be longer as compared to any rest, and therefore half-life of that particular radioactive sample measured by observer 1, 2, 3, 4, this will go on increasing. That is what the clock in motion appears to runs slower, therefore time measured by him will be smaller, and that is why the half-life measured by an observer will be shortest when for this particular, and that's what we will go for. This correct answer of this question is 0.8 c. So the observer which is moving with a very fast speed approaching towards c, he will appear or he will measure the half-life of that sample to be sample will be shortest. So as we are approaching to the velocity of light, this half-life will become smaller and smaller, or shorter and shorter. And if you are approaching, that means somehow I can extend this. If this observer is moving with velocity of light c, in that case this particular half-life will be simply equal to 0 seconds. So that is what going to be possible. So this particular case is seen to be as the case shortest and becomes 0. So that means if you are going with a speed of velocity of light away from that radioactive sample, you will measure the half-life of that sample to be simply equal to 0 seconds. So this is what a conceptual problem which is related to time dilation. So clock in motion runs slower, therefore time period measured by an observer in motion having maximum motion will be shorter, and therefore question number 10 is the correct answer. Now question 11. If an object reaches the speed of light, okay, just a minute. So question number 11. If an object reaches the speed of light, its length changes to, again this is what the same question. We are related to this formula, L is equal to L0 into root of 1 minus V square upon C square. When this V is approaching C or V is becoming equal to C, I will see that L is equal to L0, its original length, into 1 minus, now this is C square upon C square, and therefore it is going to be L0 into root of 1 minus, this is 1. So 1 minus 1 is 0, square root of that is 0. So you will get simply L equal to 0. Therefore, length of object will become simply 0 when it is approaching with the speed of the light. And that's what, if an object reaches to the speed of light, its length changes to 0. And therefore, correct answer of this question number 11 is D. So this is also related to length contraction. Length contract in such a manner that length of the object appears to be simply 0 when it is approaching to the speed of the light. Then in question 12, the length of the rod seems shorter to an observer when it moves in a specific direction. That means if I am here, this is what the rod is here, and if I am traveling towards this with certain velocity, approaching the velocity of, or with velocity, Now, because of this relativistic effect, length of this object is found to be shorter than its original one. Now, if I change the direction here, instead of going positive V, now I am going minus V. That is what we are showing here. What changes would be observed when the direction of the rod changes by 180 degrees. Either the rod is moving or observer is moving. Same is the effect. If the rod is moving in the positive V direction, its length is found to be shorter, and if the rod changes its direction and with the same speed it moves towards that particular observer in the opposite direction with the same speed, now what will happen to the length? Whether this length will appear to be smaller. So there are 4 different options given. Option A is the rod becomes even smaller. That means earlier it was of 1 meter. Then when it was going through this end with this direction, it is appearing to be 0.8 times L. Or this is L, then it is 0.8 L, and when it changes direction, it becomes again shorter, that is 0.6 L. Whether this is correct or the length of the rod increases. Earlier it was decreasing, now it is increasing. Whether it is correct, the length of the rod remains same, or the last is the rod has the length equal to its proper length. So whether L is greater or equal to L0, L is greater than L0, L is less than L0, what is the possibility? That is what here also doesn't matter whether you are moving in the forward direction or you are moving in the reverse direction, doesn't matter, as long as this relative velocity of these two objects as well as observer is same, direction may be whatever, there has to be the length contraction, and therefore this option C is the maximum correct option, that the length of the rod remains the same. So C is the option, whether you are going in the forward direction or you are going in the reverse direction, whatever length measured in motion, that will remain same even though you change the direction by 180 degrees to its earlier motion. So it doesn't matter, length of the rod remains same. That is the correct answer of this question number 12. So this is how the length contraction observed in the forward direction as well as length contraction observed in the backward direction, that is found to be just same. So whatever that particular shorter length appears in the both the direction will be just same. That's why C is the correct answer of this question number 12. Now 13, how fast does a rocket have to move relative to an observer for its length to be contracted to 95% of its original length? That is what we have to get. L is equal to 0.95 times L0. So I have this formula, L is equal to L0 times root of 1 minus V square upon C square. So write the numbers there. Therefore it is 0.95 times L0 is equal to L0 times root of 1 minus V square upon C square. I have to calculate the relative speed of that particular rocket. So this L0 gets cancelled. So this making it square, I get 1 upon 1 minus V square upon C square is equal to 0.95 into 0.95. You can go for the square of this. Therefore, simply V square upon C square is equal to, take this quantity here, this here. So this is, and change the sides again. So it is 1 minus 0.95 into 0.95. Do this calculation, 0.95 into 0.95. If it is done, 5 into 5 is 25, 2 is there. 5 into 9 is 45 plus 2, it is 47. Then 9 into 5 is 45. 9 into 9 is 81 plus 4, that is going to be 85. And when I do all this calculation, this is 5, this is 12, then this is 10, and this is 1, so it is 9. There are 4 digits, so this number comes to be 0.9025. That means I'll get V square upon C square is equal to 1 minus, this is 0.9025, and therefore it comes to be simply 0.0975. This is V square upon C square. Therefore V square is equal to, this is 0.0975 into C square. Taking its square root, I'll get, this is C, and C here, this 0.3 into 0.3. This product comes to be 0.09. So this is close to this, and therefore it is simply 0.3 C. So velocity of that particular rocket must be equal to 0.3 C. That its length is found to be observed to be 95% of its original length. That is 5% decrease will be observed when this rocket tries to move with a velocity of 0.3 c. So this problem, again same problem is there, length contraction. This type of problems can be asked in a variety of ways. Either in the percentage length change can be given, actual length change can be given, velocity can be given. So you have to just use these formulas and get the expressions of the answers as shown by this. Now next is question number 14. A particle with lifetime of 2 microseconds moves through a laboratory with a speed of 0.9 c. Its lifetime as measured by an observer in the laboratory is. So here we have to use the expression for time dilation. That is given to be t is equal to, or t prime is equal to t0 divided by root of 1 minus v square upon c square, or t. T is the time, the lifetime measure of that particular object or that particular particle in the rest frame, that is c, and this c prime is the lifetime of that particular particle which is measured in the moving frame of references. So in this case I have given this to be equal to 0.9 c. This time is this t is given to be 2 microseconds. Now this v is given to be 0.9 c, and use these numbers. Therefore this t prime is equal to 2 microseconds divided by, this is root of 1 minus, this is 0.9 into 0.9 into c square divided by c square. So this gets cancelled. You get this is 2 upon square root of, this is 1 minus 0.9 into 0.9 is, now this is going to be 0.81. Okay, and 1 minus 0.81 is 1 upon, that is 2 upon root of 0.19. So 1 minus 0.81, just go for this calculation, 1.00 minus 0.81, you will get 0.19 and square root of 0.19. Okay, so what is the square root of 0.19? If you go for this calculation, then gives this to be equal to again 0.19. Square root of 0.19 is something, or go for this calculation, you will get this calculation to be
0.16 is the square root of 0.4. 0.4 into 0.4 is 0.16. Okay, this is going to be 0.16. So this is something more than 0.4 and less than 0.5. It is something in between 4 point something. So this is going to be 0.4 something, 2 like this. 0.42 or like this is going to be square root of 0.19. Square root of 0.19 is around 0.42. So if I go for this 2 upon 0.4 or 0.42, it comes to be somewhere around 4.6 microseconds or something. So this correct answer of this question, if it is calculated, this is found to be C, 4.6 microseconds. So go for actual calculation of this 2 upon root of square root of minus square root of 0.19. You will get, so you use calculator to get this particular answer, and you will find this lifetime of that particular particle is found to be observed, and that is to be increased, and it is found to be 4.6 microseconds. So this is again, here we are using this time dilation formula to calculate the lifetime of the particle in the moving frame of reference, which is given to be 4.6 microseconds. Now this is what related to the addition of velocities. Question number 15. An atom A moving relative to the observer with velocity 2 into 10 raised to 8 meters per second emits a particle which moves with a velocity of 2.8. Now there is a correction here. This is not 108, it is 10 raised to 8 meters per second with respect to the atom. The velocity of the emitter particle relative to the scientist at stationary, that atom is moving with velocity 2.2 into 10 raised to 8, and this atom gives out another particle with a velocity 2.8 into 10 raised to 8 meters per second. So here we have to use the expression which is called as the law of addition of velocities, which is given by u is equal to u prime sorry, v plus u prime, or u prime plus v divided by 1 plus u into v prime upon c square. Now here u prime is this speed with which the moving particle is giving away this another emits a particle with B. The B particle, its velocity is going to be 2.8 into 10 raised to 8 meters per second. So this is in the moving frame of reference, and the frame of reference or the second particle that is moving away from the first particle which is giving this radiation, its velocity is going to be V, and that is 2 into 10 raised to 8 meters per second. So I can use both of these numbers very easily here to get this new velocity, or this U, the relative velocity of that moving particle which is emitted, or particle B which is emitted by A whenever it is in motion. And that's how go for this simple calculation that gives you 2.8 into 10 raised to 8 plus 2 into 10 raised to 8. So divide by 1 plus, this is 2 into 10 raised to 8 multiplied by 2.8 into 10 raised to 8 divide by, this is 3 into 10 raised to 8 multiplied by 3 into 10 raised to 8. So just go for this calculation. Now 10 raised to 8 is power same for both of this. 2 plus 2.8 is 4.8 divide by, this is 1 plus, here this 10 raised to 8, this is 10 raised to 8, this is 10 raised to 8 and 10 raised to 8, everything gets cancelled. So I'll just get here it to be 2 into 2.8 is 5.6 divide by 3 into 3 is 9. If this entire calculation is done, you will get this number here in the denominator. It is 1 plus 5.6 upon 9. This number is something more than 1. So if we do actual calculations, I'll show here how this, what this calculation gives you. This calculation gives you this is 5.6 upon 9. So I can go this to 4.8 divide by into 10 raised to 8 is there, and here it is 1 plus. So just do this calculation, 56 upon 0.9, so 5.6 upon 9. I can go for divide by this calculation. This comes to be 9. So 5.6 upon 9, let me calculate it with using the calculator. So this calculation comes to be just a second, I'll just do it in short. This is sorry, 5.6 divided by 9, it comes to be 0.62. So this comes to be 0.62, and this calculation gives you 0.60, so it is 0.62 additional there, and therefore 4.8 upon 1.62 into 10 raised to 8. If this calculation is done, once again I will do this calculation very briefly. So it is 4.8 divided by, this is 1.62. If I go for this calculation, it comes to be 2.96. So this comes to be 2.96 into 10 raised to 8 meters per second. So my correct answer, which is exactly matching with this, is answer D. So D is the correct answer, that the relative velocity of that of particle B which is emitted by atom A which is in motion from the scientist who is at rest is found to be 2.96 into 3 into 2.96 into 3 raised to 8, 10 raised to 8, which is smaller than the velocity of light. So this is not crossing the velocity of light, the limit which is put forth by the second postulate of relativity. So this is a logical answer of this question number 15, which has been calculated by using this law of addition of velocities. So how velocities are added in classical mechanics and how velocities are added in relativistic mechanics. That means in non-relative phenomenon, we can use directly algebraic methods of addition or subtraction of velocities. But in case of relativistic phenomenons, we are not supposed to use the method of algebraic method of addition or subtraction. We have to add velocities as given by this expression. U is equal to u prime plus v upon 1 plus u into v prime upon c square, and correspondingly we have to get the correct answer as shown by this example number 15. Now 16, in a uniform circular motion, there are 4 options. Uniform circular motion. Okay, this is what as uniform circular motion. Velocity and acceleration both are constant. So velocity may be constant and acceleration may be, but acceleration and velocity, these are, since these are vector, this is velocity, acceleration is toward this, both of these vectors change their sign, direction, the magnitude remains same, but the direction changes. Therefore, these are not going to be a same one. So this is not constant. So velocity and acceleration being vector, width doesn't remain constant. So this is not true. Then acceleration and speed are constant, but velocity changes. This is also not true. Both of them constant. Both of them go on changing. Neither velocity nor acceleration alone. Acceleration and velocity both change. Then acceleration and speed both are constant. So this is also not correct. So correct action or answer of this question is that velocity and acceleration both are constant. Acceleration and speed are constant, but velocity changes. So velocity continuously changes its direction, and acceleration is towards. That means acceleration is towards the center. That around which this particular object is moving. So direction of acceleration is just same, but the velocity goes on changing. Therefore, B is the correct option of this question number 16. This is the case of simple uniform circular motion, and acceleration is directed towards a center. That is called as central acceleration, or that is called as the central motion. And the velocity goes on changing. Magnitude of velocity remains constant, but its direction goes on changing. That's why this is always going to be a different vector at different locations, and therefore question number 16, B is the correct option. Now this is again simple question. Question number 17, a equation x is equal to a times cosine of omega t plus f represents. Now this represents a acceleration due to gravity. This is not correct. Uniform straight line motion. This is also not correct. Since this is a cosine function, trigonometric function, it must be a simple harmonic motion. So therefore question number 17, D is the correct answer. Actually this should not be here as a problem, but let's see what we have seen here. This is a motion of simple harmonic motion which is given by this sinusoidal. Okay, so this is the path of this object which is given by either a sine omega t plus f or phi, or like that. So I can write sine or cos for both of this, and therefore this represents a simple harmonic motion as shown by this example. Question number 18, relative to its period of the earth on the earth, period of the pendulum on the moon is. So this period is given to be 1 upon twice by root L upon G. Now same pendulum, if it is kept on the surface of the earth, and the same pendulum if it is kept on the surface of moon. So this is GE. Now on this is what TE. Now this is TM, period on moon. This is also given by 1 upon twice by root of L will be just same. Now this is will be GM. So G moon, this if it is I use this, so I can use this formula. Then T earth divided by T moon, if it is calculated, I'll get this 1 upon twice by root L will get cancelled, and you will directly get this is root of GM upon this is root of GE. We know that this gravitational constant of moon is much smaller as compared to earth, so therefore this number is going to be a smaller number. This is going to be a fraction all the time, and therefore TE is equal to some fraction into T moon. So what is asked? Relative to its period on the earth, the period of the pendulum on the moon. Okay, now that is what it's a TM. I have to go for a calculation for TM. Period on moon is equal to this period on earth divided by fraction, and whenever a number is divided by fraction we get a larger number. That shows you this TM is greater than TE. Moon, the period of that pendulum on moon is more than the period of pendulum on this earth, and therefore this is what the answer is B, longer. So relative to its period of the earth, period on the earth, the period of the pendulum on the moon is longer as given by this particular reasoning or this particular formula here. Okay, now question number 19, dash transformation is replaced by the Lorentz transformation which confirms this postulate of relativity. So in theory we learn all the time this is called as Galilean transformation. So in non-relativistic mechanics or non-relativistic physics we use Galilean transformation, whereas in relativistic mechanics or relativistic physics we have to use this Lorentz transformation. So Lorentz transformations are the Galilean transformations are replaced by this Lorentz transformation when we go from non-relativistic phenomenon to relativistic phenomenon, and therefore option A is the correct option of question number 19. Now calculate the velocity of body if its total energy is 3 times its rest. Now here we have to use this formula. So 3 times rest mass is given to be m0, and its mass in motion is given to be 3 times m0. So calculate the velocity of the body if its total energy is 3 times its rest energy or rest mass. Therefore we have to use this formula. M is equal to m0 times m0 upon square root of 1 minus v square upon c square. This is called as relativistic mass. So I can use this to be 3 times m0 is equal to m0 divided by square root of 1 minus v square upon c square. So take this quantity here. It is therefore 1 minus v square upon c square square root is equal to, simply this m0 gets cancelled. I'll get this is to be 1 upon 3. Okay, when this m0 cancelled, this is taken here. Then this is 1 minus v square upon c square is equal to 1 upon 9, or v square upon c square is equal to 1 minus 1 upon 9. See the signs, how the change changes. So it is 9 minus 1 upon 9, that is 8 upon 9. That is how we go for this calculation. That is v square is equal to 8 upon 9 times c square, and 8 upon 9 is always equal to 0.94 times c, and therefore v is equal to 0.94 times c, and therefore correct answer of this question number 20 is C. It is 0.94 times c. That means when the object tries to move with velocity approaching the velocity of light, its mass goes on increasing. This is called as relativistic mass effect. Mass of an object goes on increasing as it moves with higher and higher velocity approaching to the velocity of light. This is what its mass goes on increasing, and it becomes 3 times of its rest mass when it attains the speed equal to 0.94 c. So this has been calculated using this simple expression as given by this formula. Now this is again theoretical question. Question number 21. The relativistic mass expression is given by, okay, so there are C options are given. M is equal to m0 into 1 minus v square upon c square raised to 1 half plus 1 half. M is equal to m0 times 1 minus v square upon c square raised to minus half. M is equal to m0 times 1 minus root of v square c square raised to 1, and this is M is equal to m0 times 1 minus root of v square upon c square raised to 3 by 2. As we have seen earlier, this expression, the relativistic mass is given, mass in motion is equal to mass at rest divided by square root of 1 minus v square upon c square. So this formula is m0 upon 1 minus v square upon c square raised to half. If it is taken in the numerator, it is can be written as m0 times 1 minus v square upon c square that raised to minus half. Therefore B is the correct option of this question number 21. This is a simple theoretical question. We need not supposed to do here. Now question 22. Lorentz transformation momentum for y component. So remember, this is again a very tricky question. Answer is A, y. In the transformations, deriving these Lorentz transformations, we take this is x, this is y, and this is z, and we take another frame of reference where we go for this calculation of this Lorentz transformation. This is your frame S prime, this is frame S, this is Z prime, this is X prime, and this is Y prime. And remember, we take the motion of this second frame of reference in the direction of X only. So Y and Y prime, Z and J prime, this type Z prime, this type of, there is no motion at all in case of Y direction as well as Z direction. Therefore momentum measured in both of the direction Y and Z must be same. That's why P dash Y must be equal to Py. P dash means momentum measured in the Y direction in the frame S prime. Py is the momentum measured in the Y direction in the frame S. So that is how this type of factor gives you same correction here. And here the momentum measured in P dash X and P dash Y, they may not be same. There might be some change here according to this Special theory of relativity. But here in the Y direction there is no change in the quantities, that will be just found to be same. Therefore P dash Y must be equal to Py, and that's what in the Lorentz transformation of momentum for Y component is P dash Y is equal to Py. There is no change in the momentum in the direction of Y as well as Z. Only in the direction of Y there is change. In the direction of X there is a change. That is to be understood from this Lorentz transformation. Again, very simple question. The speed of light is E, M, Q and C. So I don't know why this question has been asked in textbook. So this is D is the correct answer. Speed of the light is C. Its number is 3 into 10 raised to 8 meters per second if I am using SI or MK system, and it is 3 into 10 raised to 10 centimeters per second if I am using this CGS system. So these are very simple numbers known to all TYBSc Physics students, so we need not spend much more time over there. 24. According to Einstein's special theory of relativity, laws of physics can be formulated based on inertial frames of references, non-inertial frames of references, both non-inertial and inertial frames of references, and D, quantum states. So out of that, as we have seen, this is what related to the first postulate of relativity. Therefore, the according to the special relativity, laws of physics formulated must be based upon both this inertial and non-inertial frames of references. Therefore, question number 24, correct answer is C. Then question 25. An object approaches the speed of light, its mass becomes, that is what, when this V is approaching towards C, M is equal to M0 divided by root of 1 minus V square upon C square. This is called as relativistic mass. This becomes M0 upon root of 1 minus C square upon C square. So this C square upon C square is 1. So it is M0 divided by square root of 1 minus 1. That is M0 upon 0, and anything upon 0 is always going to be infinity. Therefore, mass of that object becomes infinity as this velocity reaches to the velocity of light, and therefore D is the correct option, that is infinite mass will be there. So an object approaches the speed of light, its mass becomes infinite. That is what one of the special result of this special theory of relativity. Now question number 26. In relativity, an electric and magnetic fields are dependent, independent, interdependent, and none of these. So in electrodynamics you might have learned this. This is what this is called as electric and magnetic fields are called as the two sides of the same coin, and the total field is called as electromagnetic field. So that's what they are interdependent. So energy, sometimes the energy of the object or the particles in the electric field gets converted into magnetic form, magnetic energy, magnetic to electric. This type of conversion always takes place. So both of these fields are said to be interdependent, and hence question number 26, correct answer is C. Now 27. A charged particle in an electromagnetic field experiences a force which is called as the gravitational force, Lorentz force, frictional force, and the restoring force. So correct answer in this case is called as Lorentz force. So charged particle in electromagnetic field undergoes or experiences certain force which is called as the Lorentz force. Now frictional force, restoring force, these are the mechanical forces, whereas gravitational force is the different one. So Lorentz force is the force acting on the charged particle because of electric and magnetic field. Next is the same expression for that. Question number 28. The Lorentz force is represented as, okay, there are now, this is simply electrostatic. This is not, okay, this direction of this force is going to be F is equal to QE. This is electrostatic, plus magnetic force is given by this U cross B. U is the velocity of that charged particle. So Q is its charge. So Q into U cross B, this is cross product of two velocities, because this is a force which is given by a cross product of two vectors. So F is equal to QE plus Q times U cross B. So this is the correct answer of this question number 28. This is actually a problem of the classical mechanics, but we can understand it here also too. Question number 29. The Maxwell's first equation is known as, there are four different equations, Maxwell's equations you might have learned in this electrodynamics. Out of this first equation is nothing but the Coulomb's law. Okay, so this law is exactly related to the Coulomb's law. You can get study of this, or you can study this particular concept from electrodynamics, so we need not spend more time here. Then question number 30. Which of the following is the Einstein's mass energy relation? So very simple, and that is what this mass energy relation is given to be, mass energy equivalence. This is called as mass energy equivalence. Okay, that is this relation we have to write, mass energy equivalence. So mass and energy are convertible to each other. That means whenever mass is converted, energy appears. Whenever energy disappears, mass appears. or vice versa. Mass disappears, energy is generated, energy disappears, mass is generated, and this conversion between these is going to be E is equal to mc square. So don't go, these are the actual kinematic relations. Ek is equal to m minus m0 into c square, E square is equal to minus p square, c square is equal to m0 c square fourth. All the relations are true, but this relation is more appropriate for this question. Therefore question number 30, correct answer is D. This is called as Einstein's mass energy relationship. E is equal to mc square. Okay, so this is called as mass energy equivalence 2. Now question number 31, relative to stationary observer, a moving object, okay, appears to be longer than normal. B can do any of the above. It depends on the relative velocity between the observer and the object, appears to be shorter than normal, and keeps its same length all the time. So this is what a length contraction, and therefore the motion when this relative to a stationary observer, a moving object is found to be shorter than its normal. Therefore correct option is C, that is called as length contraction. Now 32, the law of conservation is valid only for relativistic speed, that means relativistic phenomenon, only for non-relativistic speed, that is non-relativistic phenomenon, both relativistic as well as non-relativistic speed, and D, none of this. So whatever may be the physics, it's a relativistic physics or non-relativistic physics or phenomenon, doesn't matter. Law of conservation is always valid, and therefore C is the correct answer of this question number 32. 33, this is what called as four-dimensional space or Minkowski space. So in Minkowski space, the fourth coordinate x4 is, okay, this is what space and time, and therefore x, y, z and t. So real and varies directly with respect to v, imaginary and varies directly with respect to v, real and varies directly with t, imaginary and varies directly with t. Okay, so this is now dimensions of this is length, and this is time. So dimensions of all this must be same, and therefore we write it to be ICT. That's what in four-dimensional space, x, y, z and ICT, then this has becomes dimensions of length, and therefore it is imaginary because of this I, and varies directly with time. C is the constant there, so ICT. So that tells you this is what the fourth coordinate in the Minkowski space is imaginary and varies directly with time, and that's why we write it to be x, y, z and ICT as the fourth coordinate in the Minkowski space. So space around us is in the we are living in the Minkowski space where this coordinates x, y, z and fourth coordinate is given by ICT, or this x4 coordinate is given by ICT. Okay, that is what question number 33, answer is D. 34, a frame of reference has four coordinates x, y, z and t, is referred to as the inertial frame of reference, non-inertial frames of reference, space-time reference and four-dimensional plane. Okay, this is not plane, actually it is four-dimensional space, or this is called as space-time reference frame. Okay, and that's what C is the correct answer of this question number 34. That is what we have called it to, just now we have called it to be Minkowski space. Minkowski space. So this is space-time, or this is also called as space-time continuum, four-dimensional space, or space-time reference frame, or Minkowski space and anything. So all these are just same. Then question number 35. The basic theorem principle used to obtain mass energy relation is, okay, Heisenberg uncertainty principle, work energy theorem, momentum conservation theorem, and then Maxwell theorem. So out of that we get this work energy theorem. So if you remember this expression E is equal to mc square, this expression can be obtained by taking this work energy theorem. That means we are changing the kinetic energy of the object, so some work is being done there, and based upon that this type of calculation shows you can calculate you can get the relationship equivalence between energy and mass by this relationship E is equal to mc square. So work energy theorem is basically used in the calculation of this or obtaining this mass energy relationship. So question number 35. 26, the lowest possible mass of particle is its. So this is what in the due to relativistic effect, whenever objects tries to approach to the velocity of light, its mass goes on increasing. So its minimum mass, lowest mass is possible whenever it is at rest. So rest mass is the mass which is called as zero speed, or the particle is at completely at rest. Then its mass is found to be lowest possible, and that is found to be the m0, or whatever symbol you can use here. So whenever this particle goes in certain motion, either gravitational mass, inertial mass, relativistic mass, all these masses are different than the rest masses, and we can calculate this as by several different formulas there. 36. Now 37, the rest mass of the photon is equal to gravitational mass, relativistic mass, inertial mass, and that is said to be d, that is 0. So these are the only particles, photons are the only particles which are allowed to travel with velocity equal to velocity of light, and therefore their rest mass and their mass in motion is identical. In fact, their mass is taken to be simply 0. So 0 mass particle is the rest mass. 0 is the rest mass of the particle which is called as photon. Out of the given several number of particles, photons are the only particles which are allowed to travel with velocity of light, and all other material particles, they must have their velocity less than velocity of light. This is again direct consequence of the second postulate of relativity, because we know that electromagnetic radiations can also be observed in terms of photons, that is wave particle duality. So only these photons which are actual electromagnetic radiations, these are allowed to travel with velocity of light, maximum velocity observed in this nature, and that's why this is another very important thing as we have discussed here. 38. Which basic law is used for the evaluation or derivation of mass variation with velocity? So here also, that is this, we see this mass variation with this velocity. So this m is equal to m0 divided by square root of 1 minus v square upon c square. This is called as relativistic mass, this is called as rest mass. So relativistic mass and rest mass are connected by this factor, and here we have to use this law of conservation of momentum principle to arrive this relationship in this special theory of relativity. Therefore question number 38C is the correct answer, law of conservation of momentum. And probably I think there are last two questions. Question number 39, which of the following were one of the conclusions of the Michelson-Morley experiment? In the beginning we have seen. So first one, all laws of physics remain invariant in all inertial frames. B, light propagates with different speed in different direction. That is also not correct. C, ether has no observable properties. And D, the velocity of light in free space is constant. So this is what the exact conclusion of this particular experiment is, this C. It has showed that there is no such ether is observed, or no ether is possible. So there are no observable properties to ether, and therefore concept of ether was completely discarded, and that led Einstein to postulate his theory of relativity, or the postulates of STR. So Michelson-Morley experiment and its importance, its conclusion, etc. is very important from the examination point of view. Now last question, as I have said here, question number 40. The device used in Michelson-Morley experiment was neither telescope nor plane grating nor prism. It was interferometer, and that is called as Michelson interferometer. So in its design, construction, working, etc., you might have seen a interferometer which is called as Michelson-Morley interferometer, and that has been used there to find out the existence of ether, and therefore question number 40 is C. So as earlier, as I have mentioned, this is the reference website for you can get it noted. This is www.sanfoundry.com. So some of the questions in this particular question bank has been taken directly from this sanfoundry.com, where www.sanfoundry.com. You can go to that website and get some more advanced question on this topic of special theory of relativity. It will help you to prepare for this examination, university examination, which is to be held in the May 2021. So thank you for patience listening. I hope this would have helped you in getting again some insights of the problems and the questions that are going to be asked in the coming examination. In this series, the third chapter, that is the partial differential equation, I am going to present this video again, but it will take certain time. Thank you all.